Hi folks, it's Chris. Welcome back again. So a few days ago I was trying to capture some of the new StarLink satellites the rocket company SpaceX put up there. I used my Skywatcher Newtonian telescope at 750mm focal length. That gave me quite a narrow field of view. With this scope, the StarLink satellites are way too fast to capture them adequately. All I could capture were stripes of light crossing the image. However, I started to wonder whether it might be possible to calculate the orbit of these satellites from that data. Okay, game on. What do we want? The orbit, meaning the height of the satellite above the ground. And what do we have? We know A. The length of the stripe the satellite left on my image. B. The exposure time in milliseconds. C. My optical setup. That should be more than enough. First of all, we will examine the information from the image. We measure both points of the satellite stripe and calculate the distance in pixels the satellite traveled on our sensor. In order to do so, we take the difference in x and y axis and calculate the square root of the sum of these squares. Why that? School math and stuff. So there we have the traveled pixels on our sensor, and we call it delta x, and is 424.078 pixels. We also have the time the satellite needed to do so. That is our exposure length, and this is delta t equals 0.163378 seconds. Given that, we can calculate something like the pixel speed, so what pixels the satellite travels in a given time by dividing those two values. So velocity equals delta x divided by delta t equals 2595.67 pixels per second. Then we need additional information, and there are two ways to get them. If you captured the satellite with an unknown optical system, your smartphone or some kind of compact camera, then take another image of stars. The exposure time may vary, but the zoom must stay the same. Then upload this image at nova.astrometry.net/upload and wait for the result. The website will give you the optical resolution in degree or arc minutes or arc seconds per pixel. We need to convert every result in degree per pixel, so you might need to divide arc minutes by 60 or arc seconds by 60 times 60 to get the desired unit degree. Or other way around, if you know your optical system, then you can use any field of view calculator online and enter your specifications. For my scope and my camera I will get 1.03 arc seconds per pixel. Dividing it by 60 times 60 will get me around 0.000286 degree per pixel. So, and 2595.68 pixel per second times 0.000286 degree per pixel gives us 0.742654 degree per second. And this is the angular speed of the satellite from my perspective. Now we can put everything together and start reasoning. So this is Earth, like this, and we are right here. The satellite is right above at a distance d and travels the length s at a time t, okay? That gives us a triangle with an angle alpha right there. The velocity of the satellite can be set as v equals s divided by t. And because we don't know s, but we have a triangle, and we can write s equals tangents alpha times d. That's school math again and stuff. And so finally the velocity equals tangents alpha times d divided by t. Let's call this our, I don't know, velocity 1 or so. On the other hand, we know the speed an object has on a given orbit. Remember, every object on a given orbit has the same speed depending only on this orbit height. That was Newton. This velocity, let's call it v Newton, equals the square root of the gravitational constant g times the mass of the central body m divided by the radius r. The gravitational constant g equals 6.67 blah 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 times 10 to the power of minus 11 meters cubed per kilogram per second squared. The mass of the Earth is 5.9723 times 10 to the power of 24 kilograms. The radius r for us is Earth's radius, that is 6,365,000 meters, plus the height of the satellite, we call it d. Okay. Given all this, we can simply set those two equations as equal. and then enter the whole stuff into a computer algebra system, because we are lazy, and let it solve to d. The result is d equals 584.275 kilometers. And is that anything like correct? Let's see. Low Earth orbit is something like 250 to 600 kilometers. And SpaceX wants to put their first series of satellites into a 550 kilometer orbit, so says Wikipedia. And so we calculated the orbit to d equals 585 kilometers, and SpaceX states it to be 550 kilometers. I'd say strike, that's roughly 6% off, but on the other hand we just used one single frame of the satellite. I'd say that's pretty sweet. I created a schematic by scale, so this is Earth, and this is the altitude the SpaceX StarLink satellites are flying. Amazingly low, I mean they do nearly scratch the mountains, don't they? Okay, summary time. Take an exposure of a satellite where it leaves a stripe on the image. Then measure that stripe, know your exposure and the optical resolution in degree per pixel, and then you can calculate the orbit height of any given satellite. You then can give an answer to the question, is it a low altitude satellite around 200 to 400 kilometers altitude, like commercial observation satellites? Is it a medium height satellite, like the GPS satellites at a few thousand kilometers? Or is it a geostationary satellite, like our TV satellites? You can give an answer now. So that's for the day. If you like this video, if you want to see more content like that, and if you want to join me on my journey through the topics of astronomy, hit like and subscribe. If you know others interested into astronomy or astrophotography, lead them here and spread this hobby, it's worth it. And most importantly, keep an eye open for situations like this, where we can take measurements and do real science. That's one of the coolest things you can do with your telescope. And as always I say, clear skies everyone, until next time here on Catching Photons.